Okay, so let's take another look at gravitational potential energy. So when we first looked at the idea of gravitational potential energy, we just said it was equal to mgh. And that actually came out of thinking about the idea of work. Work was equal to a change in energy, but it was also equal to FD cosine theta. And in the case of gravity, the force that is doing the work is the weight of the object. And so this became mg times the distance times cosine of theta. And gravity would be pulling an object downwards. So this would actually just be equal to 1. And we get our mgh. And that's all fine and well if the force of gravity is constant. Now, if we kind of zoom out and have the lens of, well, the force of gravity actually depends on how far away you are from an object, then this equation for potential energy isn't necessarily a good equation when g can change, because the further up in altitude you go, the smaller gravity gets. So we need to have a different look at this. We still have our concept of, work is equal to our change in energy, and that is also equal to our FD cosine of theta. But this time, instead of just having our F being equal to our weight, we need to have our F being equal to F big G, the universal gravitational force. So when I do that, I'm going to sub in here that my change in energy, this would be equal to big G m1 m2 over r squared. That's my force, times the distance, times the cosine of theta. Now, in our equation, r is the distance between the two objects, and in my work equation, d is the distance over which that force is acting. So they're actually the same quantity, different variables, but same quantity, so I can actually cancel that out. And you get this relationship that says the change in potential energy with big G is equal to big G m1 m2 over r. So this is a little bit different from what we've looked at before. Before, when we had constant gravity, the further away I pulled my object from like a height of 0, the bigger my potential energy got. And like there was this attraction, okay? It had more potential to fall down, more energy to get converted. If I'm looking at it in terms of how my gravity value can actually change, it's the opposite relationship. The further away you get, the weaker, the smaller the gravitational potential energy becomes. And again, this is for the case of when you have a non-uniform gravitation acting on you. Okay, so we're talking big distances, big masses here. Okay, it's the opposite relationship, and that the further you get away, the smaller the potential energy you get.